So the first few slides are going to be a little bit of review from what you guys heard from me on Wednesday. So I'm going to try to go pretty quickly. Please help our friends who were not with us on Wednesday catch up and fill in the missing pieces. When I have time, I will upload Wednesday's total PowerPoint. So here goes nothing. So when we're looking at the pH scale, we should remember down on here, the bottom here, that 7 is neutral, 0 is a strong acid, 14 is a strong base. As I go out to the right, my base gets stronger. As I go towards neutral, my base gets weaker. As I go out to the left, my acids get stronger. Towards neutral, my acids get weaker. And it's all about that percent dissociation that we talked about. So this slide is really important. I wanted you to have it so you could reference it if you needed to. Sorry, some of the graphics didn't transfer over to my my recording app very well. So some of your exponents over here on the right are a little messed up, but you get the point. So the whole point to the pH scale, which is what we are talking about today, and that's all the stuff on this side, on the right side. If I have a pH of 10, like milk of magnesia, what that means is I have 1 times 10 to the negative 10th molarity of hydrogen ions floating around in my solution. But like we talked about Wednesday, that's not the only thing floating around in that solution. You also have some hydroxides. If we look at the amount of hydroxide we have 1 times 10 to the negative 4th molarity of hydroxide ions floating around. You should notice that this number is larger than this number. So because of that, we are going to label milk of magnesia as a base. Now if we go down towards the bottom of the chart and look at boric acid has a pH of 5. What that means is that in solution, there are 1 times 10 to the negative 5 molarity of hydrogen ions floating around. So this isn't a lot, okay? We're talking about very small numbers between 0 and 1, 1 being the highest number down here at the bottom. So something that has a pH of 0 has 1 mole per liter of hydrogen ions. That's a lot of hydrogen ions. Remember, a mole is enough to hold in your hand. So if we're talking about a beaker of solution, we shouldn't be talking about super ginormous numbers. So all of our numbers are pretty small. And so we've got 1 times 10 to the negative 5th over here on the right. If I go over to the left to look at my hydroxides, that's 1 times 10 to the negative 9th. So in this scenario, my hydrogens overpower my hydroxides, making it acidic. So if I have more hydrogens than hydroxide, I'm an acid. If I have more hydroxide than hydrogen, I'm a base. And if I'm at 7, I've got equal numbers of hydrogens and hydroxides. Sorry about my slide, didn't transfer very well. Let me put this into English. When you put water down into a beaker, it starts to attack itself, and it will ionize into hydrogen and hydroxide. And so if you give him nothing else to attack, he literally will attack himself. Well, we know that if we've got the only thing in the beaker is water and it ionizes, it's going to ionize into equal halves, a hydrogen half and a hydroxide half. So if we know that all the time when we multiply our hydroxide times our hydrogen, it's always going to equal 1 times 10 to the negative 14th molarity squared. I would definitely write that on my blue notes on page 149. So if I take these two values, hydrogen times hydroxide, it always has to equal this. Then I also know that water is half hydroxide, so that's 1 times 10 to the negative 7th, and it's half hydrogen, which is 1.0 times 10 to the negative 7th. When I multiply these two together, I end up with this. We call this the Kw for water. This is the self-ionization constant for water, which is a mouthful. It's shorter to just call it the Kw. If we know in solution our total number of ions is going to equal this number, if I have one piece, I can solve for the other. This will make a lot more sense when you see an example. So on Friday, some of our classes saw this. Not everybody got to see it, and my formatting is a little off. Again, apologies, but here goes nothing. If I've got 1.0 times 10 to the negative 10th, that negative 10 leads me to believe that I've got a pH around 10. If I've got a pH around 10, I am a base. Now check out this next example. It's a little tricky. This time they gave me the hydroxide, not the hydrogen. So they're saying that the concentration is 1.0 times 10 to the negative second molarity. That would lead me to believe that, hey, my pH is 2, but it's not. Because this is OH and not H, the pH is not really 2. We have another thing called the pOH. The pOH is 2. Well, on a scale, the pH scale runs from 0 to 14, like you already know. So if the pOH is 2, I'm going to take 14 minus 2 and get 12. That is my pH. Since my pH is 12, I am a base. So you always have to look out for when they're trying to trick you. If they slide that hydroxide in, it's not going to work. The reason is because up here in the top right here, this is all about the hydrogen. It's not about the hydroxide. So we're talking about the power of the hydrogen. So if they give you a hydroxide number, you're going to have to convert it into a hydrogen number so you can identify it on the pH scale. A couple more examples. We've got a hydrogen down here of 1 times 10 to the negative 6th. That would lead us to believe that the pH is 6, and that is correct, making it acidic. And here, they tried to sneak one by with the hydroxide. But since it's times 10 to the negative 7th, it doesn't matter because we know that that means he's neutral. So now for some pH calculations. Flip your blue, page 149, over to the back. Turn it sideways so the holes are on the top, and you've got a long sheet that kind of looks just like this. You don't have to actually write the title. You'll know exactly what this is. But let me show you how to do this. Up at the very top of your page, go ahead and write for me hydrogen ion concentration. If they give me a hydrogen ion concentration, I can do two things with that. I can get, draw this too, I can get the hydroxide concentration from that number, or I can get the pH from that number. Let me show you how to do that. If I'm going from H here to OH here, I'm going to use this. The Kw is equal to 1 times 10 to the negative 14th molarity squared, which is equal to the hydrogen times the hydroxide concentration. So an example problem might look like this. If the hydrogen concentration is 6.7 times 10 to the negative 4th molarity, is it an acid or a base? Well, this is a lot harder to figure out because now my number's not 1.0. So I don't know without calculating. So the first thing I'm going to do is try to figure out how many hydroxides are there, and I'm going to compare those two numbers. So it looks a little like this. Well, I know the Kw is always going to be this. I know my hydrogen concentration is 6.7 times 10 to the negative 4th. So all I have to do is find my hydroxide. divide both sides by the hydrogen concentration, and you're basically done. The molarity cancels with the square, and so you're going to put that in a calculator and find out that the hydroxide is equal to 1.49 times 10 to the negative 11th molarity. So now, let's analyze our numbers. Which number's bigger? The 6.7 times 10 to the negative 4th or the 1.49 times 10 to the negative 11th? Well, we talked about this on Wednesday. This number here is larger, so that means that the hydrogen is larger than the hydroxide, which makes this substance an acid. Now, that was the harder way to figure out if it's an acid or a base. The easier way is to go from the hydrogen to the pH. And the way that you do that is by taking the negative log of the hydrogen concentration and so the way that would look, if I came down here, I'm going to take the negative log of the hydrogen concentration, which was 6.7 times 10 to the negative 4th. And now I've got to get that into my calculator. This is the tricky part. Please practice on the calculator when you get to class tomorrow. Make sure you're getting the same numbers as me. On your calculator, you're going to hit the negative button down by the decimal. Then you're going to hit the log button, which is to the left of the 7. And then you're going to type in your number, which is 6.7, second E, negative 4. You can close or not close the parentheses. It doesn't matter. Hit enter. And when you do that, you should get a number between 0 and 14. If you don't get that number, chances are you forgot to put the negative in front of the word log, or you forgot to put the negative in front of the 4 on the exponent. But when I do that, I come up with a pH that's equal to 3.17. So now it's really easy to determine whether he's an acid or a base, because when I've got a pH of 3, I am definitely an acid. So now let's say we were given a pH. Let's say we are given a pH of 10.79, and we want to know, hey, how many hydrogens are in that container? We're going to do the reverse of what we did to go down, and we're going to go up this time. And the way you do that is by taking the 10 to the negative pH. That looks so simple, except you need to know which buttons to hit on the calculator. On your calculator, to get that little 10 to the negative, you have to hit second, log. So it's super simple. So you're going to go to your calculator, you're going to hit second, log, and you should see this tiny little 10 pop up in this blinking square. In that blinking square, you're going to hit the negative sign. If you don't remember the negative, it's never going to work out for you. Then you're just going to shove the pH into that little blinking arrow spot, 10.79. Enter. When you do that, you get some wild and crazy number. It's 1.62 times 10 to the negative 11th molarity. So that's how many ions are floating around in the water. So let me show you the super easiest one. You're going to love this. When you want to go from pH to POH, which is down in this corner, same exact thing that we did on a previous slide. Well, we know that pH plus POH always equals 14. And so you're always just going to subtract from 14. It's the easiest thing ever. So, of course, I'm going to show my work because I'm a nerd. So it's going to look like this. If I wanted to go from the pH of 10.79 to the POH, I'm going to say 14 minus 10.79, and that's going to get me 3.21. And so then I want to go back up and find out how many hydroxides are there. We're going to do the same thing we did on the other side. We're going to do 10 to the negative POH. So in our calculator, we're going to type in second log, which gets me my 10 to the negative 3.21. And when I do all that, I get in my calculator 6.16 times 10 to the negative fourth molarity. So that's the concentration of ions in solution. Quick check here. If you look, you've got this number of hydrogens. You've got this number of hydroxides. Since the hydroxides are overruling the hydrogens, this guy must be a base. And our pH proves that. So if I was going back the other way, I would again use this formula right up here, and I should get 1.62 times 10 to the negative 11th. And if I wanted to go back down over here on this side, I would do the same thing I did on the hydrogen side and take the negative log of the hydroxide. Now, be ever so careful. Here's what you cannot do. You cannot go from H across to POH. That's a no-no. You cannot go from OH down to pH. That's a no-no. You can't cross across the big giant square. You can only go around the outside edge. In my experience, it's faster to go down and over rather than over and down. So anytime you get the opportunity to go straight down the chart, that's what you're going to want to do. If they give you something like this and they say you have a concentration of 0.025 molar and you have this acid HCl, and they say what's the pH? Well, they didn't tell you is that the H? Is that the OH? What is that? Well, because this is an acid with one H, that means that this is the hydrogen ion concentration. So to get the pH, we would say take the negative log of the H. So we would just take the negative log of 0.025 and we'd be done. And the answer to that, the pH, would be 1.60. Now, what if they gave you sulfuric acid? Now, this guy's just a little bit different because you might notice he's got two hydrogens. So that's the concentration of both hydrogens. So when I'm doing this problem, it's going to look a little different. I'm going to say the pH is equal to the negative log, but instead of just 0.025, I'm going to have to divide that by 2. And so it's going to change the pH just a little bit. So in your calculator, you could hit negative log, and the parentheses pops up, and you can type 0.025 divided by 2, and then it calculates it for you. So you don't have to divide first if you don't want to. It just changes the pH ever so slightly to 1.90. So it's still a very strong acid. The other thing they could do is they could give you sodium hydroxide. Now in this example, this is a base because he ends in OH. So if they give you a base, then this is your hydroxide concentration. So just be careful of that. If you don't get them all perfect, I'm okay. See if you can work your way around the chart. A cleaner copy for you. And it kind of shows you what to do when you're going from here, there, and everywhere. You might notice up at the top, you're always going to put the 1 times 10 to the negative 14th on the top. And you're always going to put the guy they give you on bottom to find your X or your unknown. Don't forget your negative on your log. Don't forget your negative on your pH. And this guy down here is pretty easy. And remember, never ever try to go across the square. You always have to go down and over, up and over and down, and just do whatever's shortest. If they give you the hydroxide and they want the H, it makes no sense to go down, over, and up. That's 3 steps. You could just go 1 step over. Try your best. You will be fine, and I will be back on Monday. Bye, guys.